Welcome to Quantum Control Lectures. This will be our third lecture. And before moving on to the contents of this lecture, I want to introduce the notation with which the generalized vector are denoted in quantum physics and would be used in rest of the course. They are called Dirac notation. Any vector xi is denoted as this. It says xi written in this kind of bracket, and its complex conjugate xi dagger is written as this. So this thing is called ket and this thing is called bra. So it is nothing but decomposition of the word bracket. So this is what is Dirac notation, and the inner product, if you recall, between two vectors phi and xi would be was given by this, and which is equal to phi dagger xi. In our Dirac bracket notation becomes phi and q dagger xi phi dagger xi is phi 1 star phi 2 star phi, that is complex conjugate of the components of the vector phi. Xi 1 up to xi n. So this is the Dirac notation, and moving on, we know from classical control theory that there exists a state vector capital X which describes the state of the control system and resides and evolves in a real vector space called the state space. The evolution of the state vector follows the dynamical equation, and is x dot is given by a times x plus bu, where the A is called the system matrix, B was called as control matrix. Similarly, in quantum mechanics, the state of the quantum system is described by the state vector written like this, a ket xi, which evolves in a special kind of complex vector space called the Hilbert space. And whose properties I will discuss and jot down shortly. So the evolution equation of this state vector is given by this equation, iota h bar del t of this ket xi equal to h of xi. So note, which is quite similar to the control system evolution equation. For convenience, I will write it again over here. X dot or is given by ax plus bu. So how this is quite similar to the control system equation. Obviously, bearing the control signal term, this term is not there over here. But if you concentrate only to this part, it is quite similar to this equation. Okay, and for your information, this is again the famous Schrodinger equation. So this analogy forces us to question, what does it mean to control a quantum system, or what will happen if we add a control signal term in the Schrodinger equation. This also creates curiosity in us to expand the control theory, which was till now was in a classical setting or regime, and expand it in quantum setting or regime. The details where we can add the control term will be dealt later. This analogy and the following questions were the first thing which got me hooked onto this subject since my junior year of my undergrad. Anyway, so moving on. So it's time to discuss and formally define what we mean by Hilbert space. So a Hilbert space is denoted by some calligraphic H, is a complex vector space with a inner product, which is again given by this operation in our old notation, where in the place of dots goes are two vectors, and in Dirac bracket notation is given by this, where again from the position of dots goes are two vectors. It is a operation which maps two vectors from the Hilbert space and gives complex number as its output, and this inner product satisfies the usual properties of inner product which we have discussed earlier. So again, this would be number one. If I have a vector psi dagger in the first argument of the inner product and another vector x in the second argument of the inner product, is same as if I take the x vector in the first argument and say a y vector in the second argument and complex conjugating it. Okay, or you can still imagine in the Dirac notation it is this. So there is a single bracket y. So there is, note how elegant this Dirac notation is. There is no need to put a bar or star. It is implicitly meant that we have complex conjugated this inner product. So again, second property is, as it has to satisfy, is the property that if I have an resultant vector of x and y, and in the first argument the resultant vector of this sum of two vectors x and y, and take inner product with the third vector z, is same as if I take the inner product between the x and z and y and z and add both results of the inner product. So number 3 property it has to satisfy, if I have a scalar alpha and use it to scale this vector x and take its inner product with y, then this alpha comes out of the inner product, but in a different fashion, because in a complex Hilbert space this alpha comes out as a complex conjugate of itself. So this is for any scalar alpha taken from the complex set of complex numbers or field of complex numbers to be precise. Number 4, it has to satisfy that the inner product of any vector with itself must give me a positive number, where equality holds if and only if x vector is itself is 0. So these are the 4 properties that the inner product of this Hilbert space must satisfy. Again, it is quite similar to the definition of inner product which we have discussed earlier. So this another thing called norm of a vector of any vector is denoted by this double line and enclosing this vector x, and it is defined as inner product between this vector with itself and taking square root of this result. So this the metric of h, or you can say the notion of distance in the space, that is a distance between two vector in Hilbert space H, is called a metric. So and the metric itself is defined using this norm, which is the distance between vector x, any vector x and y taken from this Hilbert space H, or you can say in Dirac notation in these two vectors. So which is given by x. This is the distance between the two vectors x and y in the complex Hilbert space. So certain properties needs to be satisfied by this Hilbert space. First is a Hilbert space is required to be complete with respect to the metric which we have just defined. Okay, this metric is required to be complete with respect to this metric, and by complete we mean, firstly we have to understand what a Cauchy sequence is. A Cauchy sequence is a collection of vectors x and has an index n, running index n, is called a Cauchy sequence if for any positive number epsilon and there is an number n, then or index capital N, such that the distance between the terms of this sequence xn and xm is less than this positive number epsilon for the indices n and m both are greater than this number or this index n. Or you can understand more intuitively if I draw a diagram, that is if I denote the y-axis as the distance between the terms of this Cauchy sequence, and in the x-axis I denote the index n or the running index n characterizing this sequence. Hence then you can understand that this as my sequence goes into higher indices, the distance dies and becomes 0. So this is what we mean by a Cauchy sequence, and a metric space H is then said to be complete if every Cauchy sequence taken from this Hilbert space H converges in H, or any Cauchy sequence of vectors of this Hilbert space, and this sequence must converge to some vector in H. So moving on, the metric space H is complete if every Cauchy sequence in H converges in H. So next property, that a Hilbert space is called separable if there exists a dense countable set X sub j. A countable set, I mean a countable set is a set having same number of elements as set of natural numbers. Natural numbers are like numbers 1, 2, 3, 4, 5, 6 up to this is also an infinite set. So if any set is having elements as same number of elements as the natural numbers, this allows us to have one-to-one correspondence between the elements of these two sets. That is, for a for one element in this set xj, the set of vectors xj, you can always attach a number, a unique number taken from the natural set of natural numbers. Okay, so this is what we mean by countable set. So coming back, the Hilbert space is called a separable space if there exists a dense countable set of vectors x, j, which forms an orthonormal basis of it such that this inner product between this x of k, x and x of k is delta xk. It is chronicle delta, and for every vector x in H, it is possible to be written in a unique way as summation j taken from the set of natural numbers x of j and the component of x along the xj basis vector. This is what we mean by a Hilbert space being separable. So now some outstanding issues and remarks before we move on to the next topic about Hilbert space. Just for the sake of completeness, a form on a complex vector space is a map. A form, a map which takes again two vectors from the Hilbert space and gives us a complex number as an output. So the inner product is defined above, which we defined above, is a sesquilinear form on H. In that it is antilinear in the first argument. That is, if we have a inner product alpha times x vector, beta times this y vector, and its inner product with the third vector z is same as if I take alpha star x z. Note this is nothing but the application of the properties of the inner product. Beta star y z. They are not exactly linear, but because the coefficients become complex conjugate of themselves, not exactly equal. So they are sometimes called antilinear in the first argument, and they are linear in the second argument. That is, if we have a vector x and some linear combination of vectors in the second argument, is same as x alpha times y, inner product between x and y, and beta times inner product between x and z. So if we have linear combination in the second argument, then the coefficients of the linear argument comes out of the inner product if we decompose this inner product as it is without getting complex conjugated. So it is linear in the second argument. So some authors tend to do the opposite. They say there is linearity in the first argument and antilinearity in the second argument, which is nothing but same thing. So this would be it. So moving on. and I will name this section as quantum mechanics. Quantum mechanics. Next, quantum mechanics laws in a nutshell. Because what we are gonna do in quantum mechanics, which is very short introduction to it, so it is, I call it, it's a nutshell, because it is very short introduction to quantum mechanics, which is quantum mechanics required for quantum control. Okay, so and you can also say we are gonna discuss only the postulates of quantum mechanics, and that would be enough for our immediate quantum control needs. And if any further quantum mechanics would be needed in the future lectures, would be introduced there and then. So let us discuss the first postulate. His first postulate is postulate 1. Postulate 1 is associated with any physical system, associated with any physical system associated with is a Hilbert space. So obviously any physical system means quantum mechanical system, has a state space where its states evolve, and that state space is the Hilbert space, and that space has all the properties of Hilbert space we have discussed just before this. So any isolated means it is completely detached from rest of the universe. Isolated system is completely described by a unit vector in this Hilbert space, denoted by this ket xi. So now moving on, the recall that inner product is a function which, or to be precise, a form which takes two vectors from the Hilbert space and gives a complex number as an output. There exists a special inner product which would be very important, is if we take the inner product between these two vectors. This vector, it characterizes the spatial position of any quantum system. Okay, denoted by this vector, and complex conjugating it to form of bra, denoted by this vector, and we have take took its inner product with the state vector xi which is a vector in the Hilbert space. Note, this is a vector in the real 3D space which we are living. That quantum system position coordinates, which characterizes and the inner product between them is again gives us a function of both the spatial coordinates of the quantum system and time. Okay, if it is located in time t naught, some place r naught, and in some future time t1 it's located in r1, so we need this time parameter also, so which is a function, and this function has a special name called the wave function of the quantum system or quantum particle in physical 3D space where we live in. And this wave function is so can be complex value. So now moving to another concept. So if I take the complex conjugate of this wave function and multiply it with itself and take a volume element, so in the physical space is said to be the probability that the particle lies in this volume element d tau, and this is true only when this wave function is normalized, that is the integration over whole space xi star r comma t xi d tau gives us this result of this integration gives me 1. This can be interpreted as a probability that the quantum particle lies in this volume element d tau only when this the integration over the whole space is 1. Note this integration, this thing is same as Mr. R inner product between R and psi and taking its complex conjugate times the xi d tau. It means that this thing, the magnitude of this complex number d times d tau is the probability density or probability per unit volume. So again I would say only when this is true, when this vector, this 8 xi is normalized, that is this the magnitude of the inner product with itself is 1. So one important example of this would be the example of quantum bit or qubit, which is given by generally a general qubit is denoted as xi a times 0 b times 1. This is 0 state and the 1 state of the quantum bit, and this xi has to be normalized, meaning this inner product between itself, which is a star b star is equal to a square plus b square should be 1, and and the probability, for example, if you want to know what is the probability that this qubit is in the state 0, is given by this inner product squared, sorry, the magnitude of squared of this inner product. So for your information, sometimes this magnitude of the inner product between 0 and xi is sometimes called the amplitude or the probability amplitude of this 0. So it's a complex number and it is called a probability amplitude that this system is in this state 0. and taking its magnitude squared, this complex number's magnitude square gives us the, which is in this case is a squared mod a squared, so which is in general called the probability amplitude, and the this magnitude square of this complex number is the probability. So similarly you can do this for the state 1. Note here that main difference between the qubit and the ordinary classical bit is that for a qubit, superposition of both the state 0 and 1 is a valid state. Okay, so before going to the next postulate, for the sake of completeness, I want us to get over with some outstanding topic that I want you to know. The first thing is the topic of linear operators. Linear operators. So I know we have talked about this earlier. In quantum mechanics, the linear map is said to be linear operators because the vector space which we are referring is the single vector space called Hilbert space, and I have told you sometimes when a linear map maps a vector taken from a vector space and gives us output of a vector which is again lies in the same vector space are called operators. Similarly, the physicists call them linear operators and don't differentiate between linear operators or linear maps. So next thing in quantum mechanics is mostly you will find the operators which we are gonna study in quantum mechanics would be bounded. By bounded I mean given two Hilbert spaces H1 and H2, a linear operator, there exists a linear operator which maps between these two Hilbert spaces H1 and H2 is a linear map from H1 to H2. It is called bounded if the maximum of this is called the supremum, the highest norm of vector which we obtain by applying this linear map on a vector in H of 1 and take its norm, and such that this norm of this vector taken from the Hilbert space H1 is 1, and the vector having output vector having the highest length or norm, which is denoted by this supremum, that we take that norm whose value is highest and take that norm as an output, and that norm is finite. This is how we say some operator is bounded mathematically. Okay, so again it means that if we apply this linear map on any vector in of H of 1, this Hilbert space H1, and this input vector is norm 1, and apply it on all vectors possible in H of 1 and take only that vector x as an output of this, which gives us this value of norm the highest, this norm, and that if that is finite, it would naturally mean that all rest of the vectors in H of 1 is finite. Okay, So then this operator capital X would be called as bounded operator. So if h of 1, h1 Hilbert space and h of 2 Hilbert space, if both of them are finite dimensional, that is they have finite dimension, every linear operator X which maps between vectors of h1 and h2 are always bounded. So in our discussion we would like to do simple example of linear operators which may become or becomes primary component in building more complex operators. Number one would be, again we would discuss what is known as bras, which you recall was given by this and was said that they are the complex conjugate of x. And if you notice, they are the simplest example of an operator because what they do is get applied to vector phi and give us a complex number. It means that it takes in vector is an operator which takes vector from the Hilbert space and gives us a complex number from the set of complex numbers. Formally, this is how a bra is defined. So we can form a case exclusively of this bras, and that space is called dual space of H, or you can simply think of the space of complex conjugate vectors of this vector xi. Okay, this is called a dual space of vector H. So if H has a countable basis, again countable, you have remembered, if H has a countable basis, then we can find an orthonormal countable basis denoted by this E of J, this set of orthonormal bases, such that we can write psi as a linear combination of these vectors. Then the bra corresponding to this vector xi would be given as alpha j star, the bra of each bra corresponding to each orthonormal vectors P of j. So next thing is the concept of outer product, which is again a crucial concept to construct operators. So what is an outer product? Given a ket xi and a bra phi, we can define a linear operator like this. Okay, if you remember, the inner product was given by this. We have just moved taken its complex conjugate of both of them and written it like this. So I think that's why they called this an outer product. I don't know, but that's my guess, as this is an outer product which is nothing but a function which takes a vector from the Hilbert space and outputs again a vector in the same Hilbert space. Then this is called the outer product of bra phi with the ket xi, because if you see that any vector chi if we apply this operator, this outer product on this, then this would be the output. If remember, this is an inner product and it is just a complex number, gives us a scaled version of this vector xi. Okay, so this another example of very simple operator. And now moving on to the third thing, then how can we form more complex linear operators? So number one technique is summing two vectors. If we have two vectors x and y, then we can construct a new operator x plus y, so, and such that this is calculated by individually applying the operators on the get xi and summing them. So this is how we can construct a new operator from two linear operators x and y by just summing them. So another way to construct more complicated operators is by using both the concept of outer product and the sum technique to form a more complex linear operator of the type phi and of the type this. So example, consider the operator phi 1 xi 1 half times phi half times phi 2 xi 2. So let's see what happens if I apply this operator on any vector xi. This would become phi xi 1 xi. This is a number, complex number, plus half phi 2 xi 2 to xi is again a complex number. So this is, and this gives us a new a vector formed by these two vectors, some scalar times these two vectors phi 1 and phi 2. This is how we get an output vector. So again, see there how we can form a new linear operator from the simple operators like outer product operators. So again we can form a new operator by my composition or by product composition or by product, which is given by x times y. That is, we first apply the y operator on this vector and then the x operator, which is now be more clear if we like this. So this is how we form complex operators from simpler linear operators. So another topic or result which is useful to know and is used in proving many relations in quantum mechanics is called the completeness relation. So what we mean by completeness relation, or it's sometimes also called as state expansion. This is nothing but if if we are given a countable orthonormal basis in the Hilbert space H, in the Hilbert space H, a countable basis E of J where 1 varies 1, 2, 3 up to whatever the dimension of the Hilbert space, and we have, if we take the outer product of each orthonormal vectors with basis vectors with themselves and sum them over all the indices, over all the possible indices, then it would give us the identity operator. Okay, this is of the dimension of the Hilbert space. This summation also runs from 1 to the dimension of the Hilbert space. Okay, it will give us identity operator. In fact, by writing psi according to this, to the state expansion, like this, if we write psi in terms of these orthonormal basis, like this operator on this psi. Note, this is an operator. Obviously, this, if you can't see this E of J applied to psi is given by J comma K the alpha K Ej in a product between Ej and Ek. And like any orthonormal basis, definition of orthonormal basis is given by Ej delta Jk, canonical delta, would be given by J again, sorry, you can write K alpha K Ek, which is nothing but psi, which satisfies the property, the defining property of an identity operator, that is, when it operates on any vector psi, gives us the same vector psi. So it is indeed equal to this sum of outer product between the all orthonormal bases among themselves is equal to the identity operator. So this is called the completeness relation, because it somehow suggests us that this set of orthonormal bases completes this Hilbert space, completely spans this Hilbert space H. So it is called because I think the outer product of orthonormal bases which spans the Hilbert space sums to identity operator. You can think that way also. So for the case of uncountably infinite dimensional Hilbert space, like a Hilbert space is of a position of an quantum particle x, which describes the position of a quantum particle which is denoted by an coordinate x, and these which characterize the state of the quantum system. If we are interested only in the position as being the state of the quantum system, then the state space of the quantum system becomes this position of the quantum system becomes a vector in the Hilbert space H. And to differentiate from the usual coordinate x, which is a real number. Remember, this is a real number, and this is not a number, it is a vector in the Hilbert space. Okay, and Hilbert space in general is complex value. This is not real. This is a fashion of writing, saying that if my quantum system is in this state, then it must be in this position x. So as we know that in our real space the x varies continuously set of real numbers, and it can have in any value. So the number, we cannot say that the set of real numbers as countable. Okay, because we can, the number of elements in the set of real numbers is not equal to the set of natural numbers, because we cannot form a one-to-one correspondence between a real number and a natural number, even though both of them are infinite sets. So if x is a position, so it takes real numbers and thus forms an infinite set. So definitely the Hilbert space of this system is a uncountably infinite dimensional Hilbert space, and such that this x of 1, that is inner product between x and x1, state x and state x of 1, or you can say this state in the Hilbert space corresponding to position of the particle in position x, and in its inner product with the state of the particle corresponding to the position in the real space x of 1, is given by del x minus x of 1, where this del is the Dirac delta function centered at x of 1. Okay, then this set is expanded as not summation but integral, because it is continuous, as xi of x d of x. Okay, because it is infinite dimensional and continuous in nature. So for those who know what a measurable set is, this R need not be, the integration need not be in the set of R. This x could take values from any measurable set omega with measure d of x. So those who know about what is measurable set and what is a measure, so for those who don't know, don't worry, we won't be dealing with any set other than real set for continuously varying variables. So now multiplying the x of 1, and on both sides this x of 1 xi of x of 1 x d of x, this is over the real number, integration is over the real numbers, set of real numbers, xi of x delta x minus x of 1 d of x is xi of x of 1, that is value of the wave function at the position of the quantum particle x of 1 in the real space, that is the space which we are living. Okay, then which is nothing but using the property of Dirac delta function, which collapses any integration and into this, because it is 0 elsewhere other than this x of 1. So this integration collapses to the single value at xi at x01 of psi at x01. So in the continuous case, is this completeness relation becomes like this, gives us this identity operator. Okay, so again you can check that it is indeed gives us is the identity operator, this thing. If you apply this to this vector, expanded vector y of x d of x, if you apply it, let me do it, won't take much time. Y of x let me denote with another. This would be equal to 1 because if we assume that this state vectors in the Hilbert space corresponding to the position x are normalized, then this would be 1 and psi x d of dx is again vector psi. So indeed this integration gives us the identity operator because it satisfies the definition of the identity operator. The last topic before going to the next postulate is the notion of Hermitian and unitary operators. I want to revisit those because in the Dirac notation we can see them in a little bit different fashion. If you recall, the Hermitian matrices are any matrix X such that if you take the complex conjugate or adjoint of this matrix, both of them are same. Similarly, the unitary matrix, any unitary matrix X is said to be unitary if the multiplication of the matrix X with its adjoint give me the identity matrix I. So that is unitary. So, but there is another way to look at them which doesn't refer to matrix representation of them and is consistent and gels nicely with the pervasive Dirac notation of quantum mechanics. So let me explain that. Given a linear operator capital X and a ket psi, we can construct a linear operator from the Hilbert space to the complex number C in two different ways. Number one, we can consider a ket such that which is formed by applying this linear operator X on the ket psi. We can consider this ket and take its corresponding bra by complex conjugating it. That would be denoted as this, and this bra is a linear operator from H to C. Second way is alternatively we can consider the linear operator this, which multiplies an element of H or the vector in H by this operator X, takes an inner product with any element, the output vector. Okay, so this output vector which we have got from the application of X with any vector in the Hilbert space H, it takes inner product with that. So this thing xi X is on application on applying it to V is given as x, where phi is any vector taken from the Hilbert space H, which is this xi x, or applying on phi is equal to xi x phi. So this is a complex number. Okay. However, both of them, they are this xi and xi outside the angle bracket. Both of them in general are not equal. If they are same for any ket xi in Hilbert space, then the operator x is said to be a Hermitian or self-adjoint. Okay, this is how we look at the Hermitian operator. So this also gives us very trivially that another way to look at the adjoint of any x. For any operator x psi, and applying this brought to this ket phi is same as xi x dagger phi, where and this x dagger is the adjoint of x. So this is the another way we looking at the Hermitian operator. So another important case of Hermitian operator is called a projection operator, which is a linear operator P, which has this property: if P is equal to P, if we apply this operator P on any vector in the Hilbert space, and is same as applying it twice in the Hilbert space. So this operator has a fundamental importance in the concept of measurement of quantum mechanics, which will be discussed in postulate 4 of quantum mechanics, called the measurement postulate. This would be it for this lecture, and I hope I am able to make clear explanation of concepts. Bye friends.